the King Kong banging on your chest. You could beat the
In this video, we are going to be talking about what we call a F-test using what? Analysis of variance, which we call what? The ANOVA. Now let's look at this. Analysis of variance is when we carry out the F-test when we have the group that is more than 2. That is, we have a set of group that is more than 2. That is the condition for what? For carry out what? The F-test, which will make use of what? The analysis of variance. If you have that 2 group, we can use that T-test or we use the Z-test, but preferably we use T-test, whether it is dependent T-test or independent T-test when we have the 2 group. But it is advisable that when you have just 2 group, go for what? T-test, which is what? Independent T-test. Now, but when you have more than 2 groups, we make use of what? Analysis of what? Analysis of variance, which will later result to what? The F-test. Now, there is what we call the sources of variation in what? In analysis of variance. The sources of variation are what? Are your treatment. Okay, we have a set of group that we want to apply treatment to. Now, the treatment is one of the sources of variation. Then there is what we call what? The error. We have the error term in what? In carry out the analysis of variance. Then we also have what we have the word total. Now, if you look at this, we have sources of variation, we have treatment, we have error, and then we have total. Now, let's just say that sum of square. Then we have what we call the sum of square for treatment, the sum of square for error, the sum of square for total. DF that you are seeing here is what we call degree of freedom. The degree of freedom means that, okay, now the degree of freedom for treatment means the number of groups that we have. Let's say I have 3 groups. Now, I have 3 groups to apply treatment to. So now the number of groups is 3 minus 1, which is what 2. That will be the degree of freedom for the treatment. Now, the degree of freedom for the total means that every total observation that I have minus 1. That will be the degree of freedom for the total. Now, the degree of freedom for error will have the degree of freedom for total minus the degree of freedom for treatment. That will be what the degree of freedom for error. Now, we go to what we call mean square. The mean square for treatment is total sum of square for treatment divided by the degree of freedom. Then the sum of square for error, the mean square for error will have what? Sum of square for error divided by what? The degree of freedom for error. So we have to go for the mean square error. Now to get the F-test, the F-test will have what? Mean square treatment divided by mean square error. That will give us the F-test, which is what we call the Fisher test. So, which is F. Now, the value that we have here, we now insert that value into our calculator to get our the probability value. And the probability value that we're having here is not the probability value that we're going to be using to make our decision. Whether we're going to reject the null hypothesis or what, we take the null hypothesis. When the time is the probability value is less than the alpha value. The alpha value is the significant value that we have. Now, when the probability value is less than the alpha value, that means that we're going to reject our null hypothesis. Otherwise, do not reject. Now, in setting the null hypothesis for what? For the F-test. The null hypothesis that we call the H-naught. The H-naught is that the mean of the first group, let me call it A, is equals to the mean of the second group, let me call it B, then is equals to the mean of the third group, let me call it C. That's the null hypothesis. Now the alternative hypothesis, which is H1, will not be, it is not equal for at least one. That means it's either mu1, mu A is not equal to what? To mu B. We have something like this, then we have mu C. We can also write it like this. Mu A is equal to mu B, but it is not equal to what? Mu C. It is equal to mu A is equal to mu B, but it is not equal to what? To mu C. That means that it is not equal to mu C. And the one thing about the analysis of variance is that whenever the one is not equal to the other, if it is just one out of the two is not equal, it will reject everything. That means that it's not equal. So we can also have that the mu1, mu2, mu3, and mu1, mu2, mu3, it is not significant. Then the H1 will not what? mu1, mu2, mu3 is what? Is significant. Let us take the example and let us see how we can make use of this. Now we have a problem to solve. Look at that table. In a study to compare the antibacterial activities of extracts from 4 plants, a researcher randomly selects 5 participants. That is A, B, C, and D. They selected 5 participants per plant. Supposedly they affected by the bacteria. A few days after the administration blood specimen was taken and bacterial loaded estimated. So we have the value for that. Now, the first thing, what is our non-hypothesis? The non-hypothesis is that the participant mean bacterial load were the same across 4 plants. That means the mean 1 is equal to the male is equal to mean B is equal to mean C and is equal to mean D. Then the alternative hypothesis will not be what? Participant mean bacterial loads were not the same for at least a pair of plants. Now, look at this. We have the first participant. This is the plant A. We have the source. Then the total means that we have everything together, we have this. Then the same thing for plant B. We have everything, we have it together, we have to have this. The same thing for plant C. We have everything together, we have to have this. Now, there is what we call the grand total. The grand total means that if we sum this one downward, 10 plus 15 plus 35 plus 40, it must give you the same thing when you sum this down, 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 when you sum this down. When you sum everything here, it must give you the same value as this. So when we sum everything here, we're going to have 100. When you sum everything here, we're going to have 100. This is what we call the grand total. Now, in analysis of variance, there is what we call a correction factor. Then the correction factor is what? The correction factor, we call it CF, means that the grand total square divided by the total number of observations, which is n. Now the grand total here is 100. So 100 square divided by 20. So we are going to have what? We are going to have 500. We are going to have 500. 100 square divided by what? Divided by 20. We are going to have what? We are going to have 500. Now, there is what we call in our analysis of variance table, there is what we call the sum of square total. Now, the sum of square total simply means that the summation of all the observation square, 1 square plus 2 square plus 2 square plus 2 square plus 3 square plus 2 square up to 9 square, then minus the correction factor. So now, we are going to have 1 square plus 2 square up to 9 square, which is the last value here, minus the correction factor, which is what? Which is 500. So if you do just this, the square of everything here, we're going to have 638. Then minus what? 500, we're going to have the sum of square for total is 138. Now we move to what? Sum of square of error. The sum of square error means that the treatment that we have, this is the treatment in group A, the treatment in group B. So we're going to sum this like this. We sum it to the row wise. So when you sum this to the row wise, so that means that we're going to have the I. We're going to have IA, I dot. We are summing it to the row wise, I dot. So that means that you sum this to the row wise, we have 10. The 10 divided by how many of them here will we sum together? 1, 2, 3, 4, 5 divided by 5. If we sum this together, we have 15. Divided by how many observations? 1, 2, 3, 4, 5. We have this. The same thing for this, the same thing for this. Then minus what? The correction factor. The correction factor is very, very important. So once your correction factor is wrong, that means that everything that you're doing is wrong. So by the time you do this, we're going to have 130. Now, the total, the SS total, the total sum of square, SS total is equal to SS treatment plus SS error. So now, by the time we make sum, the SS error is sorted for the formula, we're going to have sum of square total minus sum of square treatment is going to give us what? Sum of square error, which is what? We have 138 minus what? 130, which is we have 8. So we have, now we have sum of square for total, we have sum of square for treatment, we have sum of square for error. Now, we move to what? The degree of freedom. Now, to get the degree of freedom for total, the degree of freedom for total, for that one, is total observation minus 1. And don't forget that the total observation n is equal to 20. So minus 1, we are going to have 19. So the DF for what? The degree of freedom for what? For total is what? Is 19. Now, the degree of freedom for treatment, how many treatment do we have? 1, 2, 3, 4. Don't forget that the degree of freedom for treatment, we're going to have what? We're going to have the number of treatment, which is what? T. Our T here is what? 1, 2, 3, 4. We have how many group? 1, 2, 3, 4. 4 plus, so 4 minus 1. So we're going to have what? Which is 3. So the degree of freedom for the treatment is what? Is 3. Now, to get the degree of freedom for error, it will be the degree of freedom for total minus the degree of freedom for what? For treatment. So we're going to have 19 minus 3, which we're going to have what? We're going to have 16. Now 16. So the degree of freedom for error is what? Is 16. So let us present all these values in our what? In our ANOVA table. So now when we represent, we put all our data back into the ANOVA table. So we have the treatment, we have the error, we have the data. So the sum of square for treatment that we have is 180. Sum of square for error is 8. Sum of square for data is 38. Now the degree of freedom we have 16 for error. Error is 16. Then the total is 19. Now, to get sum of square, you get the least square. 130 divided by 3, we're going to have this. 8 divided by 16, we're going to have 0.5. Now, to get our the F will now be the MS treatment divided by MS error. So by the time you divide this by 2, we're going to have this. Now, if you put this value, your p-value, your calculator, your probability value, so we're going to have our probability value to 0.0000. So now we make our decision. We reject the null hypothesis if the F calculated is greater than the F calculated. That is, if the probability value is less than the alpha value, which we have our alpha to be 0.05. Now, since the p value is 0.00 is less than the alpha value, which is 0.05, we reject our null hypothesis. That means that the what? We reject our null hypothesis. Then what we call the decision rule. We have the decision rule, we have the decision, and we conclude. Now the decision rule is that reject the null hypothesis if the F calculated is greater than what the F calculated. We reject the null hypothesis. Now, or if the p value is less than the alpha value, we reject the null hypothesis. Now we go to the decision. Now since the F calculated, which is this, is greater than the one check our two bottom value the probability value. Since our probability value is 0.00 is less than the alpha value, which is 0.05, we reject our null hypothesis. Now, if we conclude that at least for one, the mean of one is not equal to the other. But if we want to conclude based on the hypothesis, then we conclude that that the participant mean bacterial mood were different from at least a pair of plants at our alpha of 5%. That means that the mean of one of the 4 plants that we have, the mean of one is different. So that means that we're going to reject our null hypothesis, and then we conclude. Thank you very much. See you in the next one.